Hello, my friends. Welcome to another day, exciting day, not just a day, exciting day of discrete mathematics. Today, we're going to be continuing where we were last time, looking at Euler networks. We're going to be talking about something called Eulerization. This idea of Eulerization is what really happens when we're considering an Euler circuit. Now, not everything, as we've seen, some graphs have an Euler circuit, and that happens when every vertex has an even degree. We've seen that some graphs have an Euler path, and that happens when we have exactly two vertices with an odd degree. But for everything else that has more than two vertices with an odd degree, there is no possible Euler path. Now, in the real world, things that would need to consider an Euler circuit would be like your postal delivery. The post truck just leaves the post office, drives all around town, up and down every street, delivering mail, and the idea is they don't want to repeat those streets, so they're going to try to create a circuit and then get back to the post office at the end of the day. School bus leaves the bus yard, picks up all the students on every single street, traveling each street, ideally one time, and then returning to the bus yard at the end of the day. The garbage delivery, same thing. But in reality, there are cul-de-sacs, there are dead ends, there are odd intersections. There are streets that we don't actually need to go down because no students live there or no people live there, so we don't need to deliver mail. In these instances, where we do not have a circuit, and instead we want to make a circuit, we go through this process of Eulerization. So here's our situation. Over here on the right, I've got this map of our hypothetical town. Our antagonist lives at A, wants to create an Airbnb, and kind of promote tourism, wants to say, hey, take a drive around our wonderful town, visiting all the sites, visiting all the streets exactly once. Now, we can look at this. We've got the school over here. We've got the farm over here. We've got the supermarket over here. We've got the shopping plaza over here. We've got the hospital over here, etc. Can we drive every street in our town exactly once without repetition and get back to our starting vertex? We want to make this a circuit, in fact, an Euler circuit. And what we can do is take all this information. I don't actually care where the farm is, where the hospital is, where the school, anything else. We're going to take this and distill it down to its essence. We want just the necessities. So we're going to take our town and turn it into a graph. So here, we're going to help our friend Annette create a graph to model the roads and intersections in this area below. In our graph, each intersection is going to be represented by a vertex. That's a point where we can change roads or we can change directions. So here, all of our intersections, all of our street intersections are going to be a vertex. I've already got the points already laid out. Each road that connects those vertices is going to be represented by an edge. In graph theory, we don't actually care about distances. We don't actually care about kind of the physical arrangement. We care about the locations and how they're connected. So you can see the image here is a little bit kind of faded out. I don't actually care about what the pieces are. I care about how they're connected. So I'm going to create a graph by using edges to connect those vertices that are connected in the real world. So we know that we've got a road from A to B. I'm going to represent that with an edge. I've got a road from B to C, and so on. So I'm going to go in and draw all of my edges. And the resulting image is going to be our graph. By looking at just a graph, I don't care about the direction or where I'm going. I care about how things are connected. And then we're going to apply Euler's theorem to determine, do we have a circuit, do we have a path, do we have neither? You may have noticed that right in the center there, that L, H, J, and K, well, those were curved roads. I could follow the roads. I can also just draw a straight line. I care that L is connected to H. I don't care the distance there or the curvature of there. I could draw a squiggly line if I wanted, and it's connected to H. I just use a straight line because it represents the shortest distance right there. So that blue outline, along with our vertices, our points, that's our graph. That's the essence of what we need. Now, if we look at this, can we start at A and take a trip around all the town, crossing every single edge exactly once? Well, we're going to apply Euler's theorem. Euler says if we have every vertex is of even degree, meaning there's an even number of edges coming out of each vertex, then we've got a circuit. So let's go ahead and count the number of edges coming out of each circuit, out of each vertex. There's 2 edges out of A. There's 3 edges out of B. There's 2 edges out of C. I'm going to keep going. 4 at D, 3 at E, 4 at F, 3 at H, 3 at J, 3 at K, 4 at L, 3 at G, 2 at M, 3 at N, 2 at P, and 3 at Q. So we have here, I'm going to highlight these. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 odd vertices. Therefore, no path and no circuit. And I am, of course, speaking about an Euler path or an Euler circuit. So down at the bottom of this page, how do we know why it's impossible to have an all-around town adventure, starting at point A, traveling every street exactly once, and then returning to a nest A or B and B at point A. Well, Euler's theorem for graph theory says if we have more than two odd vertices, we don't have a path and we don't have a circuit. But in reality, you can drive around town and you can get back. What we're going to have to do is repeat streets. So this, I'm going to go into the next section, is if we forget about that rule where we cannot repeat a street, we want to get around and get back to home at A. How can we do that repeating as few streets as possible? Jumping ahead, this is going to be our process called Eulerization. Eulerization, identifying all of those odd vertices and repeating edges, not creating new edges, repeating edges on a graph to build an Euler circuit. So once again, we had 1, 2, 3, 4, 5, 6, 7, 8 odd vertices. What we're going to do is I'm going to use a curved line to indicate I am repeating an edge, and I already have this set up with edge EB as an example. Before, we had one edge connecting E to B. They're both odd because we each have 3 edges coming out. What we're going to do is you can see I've added an additional one. This represents a repetition. So we are repeating that edge. What that does now is if we count the number of edges coming out of B or E, we've got 4. At each, by repeating that edge, we've added 1 to each of those vertices and made them even vertices. That's the idea here. Let's find another pair of vertices. So H, we could connect H to K, and I would have to repeat the road to L, and then the road to K. I could connect H to L and go up. But I want to do this with as few repeated streets as possible. There's my instruction. I want to do this with repeating as few streets as possible. So H and J are right next to each other. I connect those two. There's a repeat. I notice that K and Q are next to each other. There's a repeat. Oops. And I notice that I'm remaining with G and N. Now G and N, I cannot draw a line right through. That's not acceptable. We are not creating a new road. We are going to be repeating roads. Let me get rid of that. And if we look at our town underneath, we don't want to drive over the cow. So instead, we can repeat G to L. What that does is now adds a 4th line into G, making that even. Unfortunately, it adds a 5th line into L, making it now odd. It's in a way move the odd vertex down a step. Now we're going to repeat N to L. So in that case, we had 2 repetitions. I don't know why my lines keep them disappearing. We've added 2 to L, and even plus 2 keeps it even. We've added 1 to N, making it 4. So now, if we look at all of those vertices that we added an edge to, everything is now even. We're going to have a circuit. So what characteristics of the end vertices made it so these edges needed to be repeated? They were odd. By adding an extra edge or repeating the edge, we've now added 1 to an odd number, making it even. So this process, we call it Eulerization. We're identifying and repeating the least number of edges on a graph to create an Euler circuit. So first of all, we're going to identify all of our odd vertices. In the graph that I have here at right, A is an odd vertex, D has 4, E has 5, because the loop counts for 2, B has 4, and C has 2. So we have 2 odd vertices. I'm going to pair each of those odd vertices with another odd vertex close to it in the graph. In our example up top, we looked at E to B, we looked at H and J, we looked at K and Q, and we looked at N and whatever's there up at the top. In this example, we're going to connect A and E. Now we're not going to draw a line straight to them. That does not work. We're going to be repeating edges. So step 3, for each pair of odd vertices, find the path with the fewest edges connecting them. So I would go A to D, and then D to E. That is now added 1. So since I had 1 plus 1, we now have 2. I've now added 1 to E. Since we had 5 and we've added 1, we're now at 6. Everything's even. That makes it an Euler circuit. That is Eulerization. Thanks. We'll see you later.